This video is on residuals. A residual is how far away an observed value is from what is predicted. By the regression equation. So an observed value is what you actually see, the data values that you get in a table. The predicted value is the value you get when you plug in the x value into the equation you get from the regression model. This can be done with linear, quadratic, exponential, any type of function that you can do with regression. A residual is also, you can think of it as a residue left over. A perfect residue would be when you take a sticker off of a desk and there's nothing left on, then that's a perfect pull. There's no residual left over. But if you pull a sticker off of something and there's a whole bunch of stuff left over, that means it was not a good fit and therefore you had a lot of residue. So a residual can be calculated with how far away it is from the observed value from the predicted. We can take the observed value and we can subtract the predicted value. So hopefully this value will give you 0. If you have the observed value minus the predicted, hopefully you'll get 0 because that will be a perfect pull and there will be no residue left over. So if you're looking at the sum of all of the residual values, as in if you have 10 data points, all of the residuals should add up to 0. And now it might not be exactly 0. It should be or very close. Because of rounding. So what this will look like is if we have a line of best fit. Let's see, this is our line, and we had data points that were close to the line, but they don't fit perfectly. There's a little bit of residue. The residuals are the values between the data point itself and the line of best fit. So these are positive residuals because they're above the line. So all of these are positive residuals. But then you also have the values that are below the line, which are considered negative residuals because they're negative values. So what should happen is these values, these positive values, added to these negative values should become 0 because it gets us back to the actual line. Now what a residual plot will show is if a regression model fits the data appropriately. And again, residuals can be used to compare the quadratics and exponentials and linear. So that is what residuals are used for. It's actually, residuals are the only way to compare different types of functions. For example, if we want to compare linear and a quadratic function. Or if we want to compare a quadratic function with an exponential function. So residuals are the only way you can compare two unlike functions. You might have seen that you can use the correlation coefficient for linear functions to determine if it's a good fit. However, there is no correlation coefficient for a quadratic or an exponential. So residuals are the only way we can compare different types of functions. So for an example here, we're going to create a residual plot for each set of the data. So we have our data here. We have our x's and our y's. It's already been plotted. And we've already done the linear regression equation. So this is a linear regression. And the equation is y equals 0.455x plus 0.683. So this has all been done in the calculator for us. So the observed value right now at x of 3, the observed value is 3, the observed y value. When x is 10, the observed y value is 4. That's the actual data that we see, the scatter plot. So the predicted value is when we use the x value. So we're going to use the x, and it's from the best fit line, or from the linear regression equation in this case. It's from the regression equation. So what this means here is that we're going to utilize this x value to figure out this value here. So we're going to use, down here, I'm going to use the value of x. So x is equal to 3. I'm going to plug 3 into this regression equation. So y equals 0.455 times 3 plus 0.683. When I plug this into a calculator, I get out the value of y equals 2.048. So our predicted value here from that line of best fit is actually 2.05. I'm just going to round that to 2.05. So I can do the same thing for each of these. So with my x value of 10, I'm going to plug in, and I'll get that the predicted value is 5.237. I'll plug in 15, and I'll get 7.513. Then I'll get 9.790, 12.067, and then the last one is 14.344. And as you can see on the predicted value, they are slightly different from the observed. So the 3 is the actual data, but the predicted value was going to only be 2.05. The actual value was 4, but the predicted from our line was going to be 5.237. So you can see that they are slightly different. And that is what the residual is. The residual is how much is either left over or too much. So to find this, we do our observed value minus the predicted value we just got. So our observed value here was 3, and our predicted was 2.05. So I'm going to subtract that. So 3 minus 2.05 is 0.95. It's not a big difference, and that's good. The next one was observed value of 4, but the predicted value was 5. So when I subtract that, the actual data is below the line of best fit. So our data point here is actually below this line of best fit. So it's going to be a negative 1.237. Now do 9 minus 7.513. We get 1.487. This next one is the data point is truly below what the predicted value is. So it's again below that line of best fit. So it's going to be a negative 2.79. And see, these are a little bit bigger compared to that first data point. So the next one, 13 minus 12.067 is 0.933, which is below 1, so that's good. And then the next one, 15 minus 14.344, and we get 0.656. So if we were to add these together, then it would should be close to 0. It might not be perfectly 0 because of the rounding. Now, all of these residual values, I'm going to make a little note down here. All of these residual values are actually pretty close to 0, which kind of tells us that what this linear regression is a good fit. So all residuals are close to 0. So linear is a good fit. Now we can actually plot this on here, and I'll use this as my x-axis. My x's go from 3 to 30, so I'll count by 5s. So I'll do 5, 10, 15, 20, 25, and then I'll put another line out here to be 30. And then my y values, my y observed values go up to 15, but the residuals is what I'm plotting. And my highest residual is negative 2.79. So I'm going to count by 0.5s. So this is 0, 0.5, 1, 1.5, 2, and then 2.5. Now do the negatives. And then I will go and plot our residuals. So at the x value of 3, because this is still the x value, the y value is your residual values. So at the x value of 3, my residual is at 0.95. So this is about 3 right here, and it's a little bit below 1. So here's my residual point. The x value of 10, my residual is at negative 1.237. So about here. X value of 15, I'm at 1.487. X value of 20, I'm at negative 2.79. So I have to go below the negative 2.5, so about right here. 25, I'm at 0.933, so right below the 1. Then at 30, a little bit above the 0.5. So these are our residual values and the locations of them. So as you can see, they're all kind of scattered closely to the x-axis, which is what we want, and there's not a big discrepancy between them. Now, if anything, this is your largest value that is out of place. So if we wanted to make a better fitting line or a better fitting equation, then this data point, which had that negative 2.79 residual, so the 20,7, might not fit that data very well. So this residual value right here probably is the spot, or that, this data point probably is a spot that we could take out and make a better fitting equation. So that's another thing you can think about.